So the goal of our day, so let's start by defining a goal for a day of our class. We want to have like one particular goal that we want to achieve at the end of this class. So if we were given a wing, right? If we were given a wing or airfoil design, what are the natural frequencies of this? What are the natural frequencies? And B, what is the critical clutter speed? If we are able to determine these two quantities, then we should be able to use this information to make our designs more robust. Okay, let's start by looking at what are the challenges in dynamic aeroelasticity. It is very hard to predict, primarily because there's a lot of unsteady aerodynamics involved. For example, like gust. We cannot predict when a gust would come in. And it needs to be designed for these kind of phenomena that are harder to predict. And since they're difficult to predict, they're also difficult to design against. So what do we mean by unsteady aerodynamics? For example, when we look at the flow around the airfoil, let's say if we have an airfoil, let's say, and now there's a flow around the airfoil. Right? So this is our airfoil that we have designed, and then there's a flow around that with some velocity v u. Now this velocity is changing with time. It's not constant velocity. When we did our static aeroelasticity, we assumed that there's a velocity v that is of the airflow. And this is no longer the truth, right? So when we are looking at actual scenarios, the air velocity, airflow velocity is not constant over time, but it is changing. This affects the dynamics of the aerodynamic surfaces that we are going to design, like airfoils. And since the airfoil surfaces are affected, it in turn affects the flow that is surrounding the air. Right? So there's a loop here. So the velocity is changing, which affects the airfoil structure or the dynamics of these airfoil structures. And because these airfoil structures are changing, that affects the flow velocity and vice versa. So this is occurring over time rather than instantaneous. When we did our quasi-static aerodynamics, we assumed that the changes in the aerodynamics are instantaneous, so the structures are rigid. But when we are actually looking at unsteady aerodynamics, this would change. So there are various ways of accounting for these. A second challenge is that these flutter events, that's one of our focus today, is a very violent and unstable event. It's an unstable oscillation. And these can lead to catastrophic events like fracture and failure. So one needs to also account for some of these materials, nonlinearities and material difficulties that come in when designing these structures. So there are some ways of looking at the unsteady aerodynamics. So how do we look at these unsteady aerodynamics? Let's say, so for example, if we think of the functions in unsteady aerodynamics. So first one is known as the Wagner function. So what's the Wagner function? It assumes that the change in the aerodynamic force over a period of time is a function of time. So let's say for aerodynamic force, we had an aerodynamic force, let's say called F, is our aerodynamic force. So then we can say F is a function of time. It's varying with time. Second one is Theodorson function. Here it assumes that the aerodynamic force acting on the wing is harmonic but lacks the oscillations of the wing. Thus it's a function of frequency and involves complex aerodynamic derivatives. Here we are saying that the function aerodynamic force is a function of the frequency, right? So it's the frequency of vibration. Right? So there are various functions to account for these kind of unsteady aerodynamics that are often used in these calculations. As we go through the lecture today, we will try to start with a very simple scenario and then see how we can look at more complex scenarios as we go on. So let's start with one of the most important phenomena that people look at in aerodynamics or dynamic aeroelasticity. So this is essentially Flutter. Most of you have already seen some videos of Flutter which in the initial starting class when we introduced the ideas of aeroelasticity. We looked at some videos of this Flutter where the bridges were suddenly galloping and then suddenly breaks. The Tacoma Bridge collapse is one of the very famous examples, right, that we saw, Tacoma Bridge. So there were various other events of aeroelasticity, from ranging from aircraft wings, we also looked at wind turbines, dynamic aeroelasticity and flutter could also occur in, for example, turbine blades. And so on. So lots of places where this can occur. One of the things that was very common in some of the videos that we looked at Flutter was that it was catastrophic in nature and had a devastating effect. It was catastrophic, right? Second thing was that what was happening in there was an instability that was there in the structure, and it started extracting energy from the airstream so that it oscillates with a negative damping. It was not damping, the vibration was not damping, but it was increasing continuously. The amplitude of oscillation increased with time, and after a certain time, the structure could no longer tolerate this kind of a large deformation that it fails. And this self-destruction occurs very quickly once the oscillation with negative damping was initiated. To some extent, if I'm going to plot it here, let's say if I would plot with time versus, let's say, the amplitude, crudely we could say that there was a small oscillation and suddenly there was a very large oscillation, right? So this was what we could think about. So there was the system was extracting energy from the air stream. Was extracting from airstream. There was some negative damping, and this negative damping led to the oscillations increasing with time, or the amplitude of oscillations to increase with time. And this is what led to some of these self-destructive events. Okay, so just to think about when we intuitively think about when flutter could occur, or what would be our critical flutter speed. As our speed increases, the damping ratio starts to increase, and there's a certain point at which it starts to decrease, which means there's also a velocity at which the damping ratio comes to zero. So there should be a velocity at which our damping ratio is now zero. So this point at which damping is zero is what we call as a critical flutter speed. Here we are plotting our damping ratio versus the velocity, and then any further increase in the velocity would only lead to a negative damping ratio. As long as our damping ratio is positive, that means that the system oscillations in the system will damp out to zero. As soon as the damping ratio becomes zero or negative, the oscillations will start to increase very violently. And that is an intuitive way or mathematical way that we can find what is the point at which flutter occurs. An aircraft designer should be able to demonstrate by documentation of design work and testing that the flutter speed is at least 20% above the dive speed. In order to get your designs through, that is a very important criteria, simplistic criteria to see that the flutter is not going to occur when in these dive speed ranges. Okay, so let's start by looking at the problem of classic binary flutter. We will try to explain what this is as we go on. In the meantime, let's just try to write our original aerofoil that we had and name the different parts. If you remember, we had a flexural axis. So we have the flexural axis. So that's or the elastic axis about which the elastic deformations are taking place. Then we have the aerodynamic center. So let's say call it AC. If you remember, the aerodynamic center is the one about which we have some lift and moments that are acting. So let's say MAC. I'm writing this so that you have the time to think about this and maybe recall what you have already studied in your class on aerodynamics. And so we assume that initially we had let's say airflow at a speed of v. I can just show you an image, but we take this time to also think about what does this mean. And then we had initial angle of attack. Let's say we call it theta naught, or this is our initial angle of attack. Further, we have defined something called a semi-chord. And let's say the distance is b to the end of the airfoil on either side. Let me just move this a bit here. Or I can probably move this. Or ploops or flexural axis. And our semi-chord length B. Okay, and since we are looking at aerodynamics here and we are looking at dynamic aeroelasticity, we also want to understand how the inertia is playing a picture. So we also have, let's also define a center of mass. As we did last time, we originally had a spring here that allowed for our pitching motion. Let's call the spring stiffness K theta. Along the pitching motion was basically this kind of like a rotation or a torsional motion. In addition, we are saying that we also have a heaving motion, that is up and down. So the airfoil is not just doing this, but it's also doing this in a way. Right? As we saw in some of the Flutter videos, if you remember, the wings were not just doing the torsional motion. they were also going up and down. So it was a combination of both, right? Or in other words, we can think of this as a 2 degree of freedom system, if you think of it. So let's say we have another spring here that is controlling the heaving motion. So let me call this as Kz. And I would define my Z as in the downward direction with the 0 on the elastic axis. We have also in the previous class, if you remember, we defined the distance between our elastic axis, or flexural axis to our aerodynamic center to be E. We call this the eccentricity. Similarly, let us define our distance between the elastic axis or flexural axis to the center of mass. Let us call that as Bx into A. And similarly, distance between the semi-chord to our elastic axis as B into A. Here A and XA are some form of a non-dimensional numbers. We are thinking of it as a fraction and saying when we multiply by the distance semi-chord distance B, that is our distance that we are getting. Or in other words, if we just try to write it here, let's say this distance is nothing but B into A, and this distance is our B into X into A. Let's take a moment to think about it here, all the things that we have, and we also from the semi-chord, let's also define a distance X. Okay. So we are defining our X and Z coordinate, and we are also defining some of the distances that we have. And so we have defined these distances. We have defined the flexural axis, aerodynamic center, center of mass, defined the distances between them. Aerodynamic center, as we know, is the place where the lift and the moments are acting. And the elastic axis is where, or flexural axis is where some kind of a pitching and a heaving motion is controlled. Okay, or let's say we kept calling this elastic axis. So let's write that down, elastic or flexural axis. And let's take a moment here to think about this as we proceed ahead and how to use this. In order to, our goal is to determine, we have this pitching motion, the heaving motion and the pitching motion. So this is what's happening. So it's a complicated phenomena. How do we take this and decouple them into looking at this as like a 2 degree of freedom system, maybe a coupled or a decoupled 2 degree of freedom system? How are our equations of motion, and what does this equation of motion mean? Right, so we write an equation, but what is this equation meaning? And then we also, one other thing that we probably want to define is that because of this pitching motion, there's a change in the angle of attack, right? So there's a change, small changes in the angle of attack, and we also want to define the change in the angle of attack. So if we say there's a change in the angle of attack here, this is our change. So let's call this change in the angle of attack as theta. Okay, so there's our change in the angle of attack. So let's use all of these ideas in order to define how we would use this to calculate when the flutter occurs and if it would occur. As we have done so far, we will try to first start by writing our Lagrange equation and to derive our equation of motion. And so let us assume that our Lagrange equation, there's no dissipative effects. Let's say d is 0. So if we say d by dt of dt by dz dot minus dt by dz plus du by dz equal to, let's say, qz. So z is our heaving motion, that's our up and down. Okay, so and then we have our pitching motion, which is the theta. So we have two motions here, one is the heaving motion and one is the pitching motion. So we can write that d by dt of dt by d theta dot minus dt by d theta plus du by d theta equal to some q theta. Let us try to go, and we also remember what is the q, z and q theta. These are our generalized work terms. These are our generalized work. So we can say q, so we are saying if there's some small virtual work done, what is coming out of that, right? So if we have some virtual work, del W, small virtual work is done due to small heaving motion in the z direction, or some virtual, what's the rate of change of the virtual work done when there's a small change in the pitching motion, d theta. And we also know that T is nothing but our kinetic energy, and U is our strain or potential energy. Right? And just to complete, for completeness, we can say this represents our heaving motion, and theta represents our pitching motion. Okay, so we have this completely in there, and our goal, as we have done in the previous classes, is to determine each of these terms so that these can be substituted into the Lagrange equation, and we would be able to get our equation of motion from there. So let's, in order to calculate our kinetic energy, we need to first start by calculating the velocity. For example, our kinetic energy is nothing but half m into v square. So we need to calculate the velocity. There are two motions here, as we saw. One is the heaving motion, which is basically causing the airfoil to go up and down. And then there's the pitching motion, which is basically the torsional motion. So basically, it's not just a single one, but it's like a combination of both, right? So we want to write them out separately and then see how they are both coupled. The heaving motion, let's say, is that as we saw in our airfoil, our displacement is nothing but, let's say, z. So if we look at z is our displacement. That's our controlling, that is quantifying our heaving motion. So it's moving in the z direction, up and down in the z direction, right? So we can say that the displacement, because of the heaving motion, can be defined as z. That means that the velocity can be defined as dz by dt, or rate of change of the displacement, or that is nothing but z dot. The second motion that we have is the pitching motion. That is a torsional motion. Now we want to know how much is the aerofoil moving. We know because of the heaving motion how much it has moved and what's the velocity in the vertical direction. But we also have some pitching motion that's also contributing to the airfoil to move, or each segment of the airfoil to move. And so we want to understand what is this pitching motion as well. And so if we look at it, initially we assumed that the angle of attack was theta naught, and then it was changing by theta, and this theta is varying with time. We also defined the distance x here, which is from the semi-chord. So from the semi-chord, the vertical displacement of any point on the airfoil would be nothing but x into theta. How did we assume that? We assume one of the things that we have made an assumption is, let's assume that our rotations are small. Let's assume small rotations. Right? So then the vertical displacement due to pitching nothing but x into theta. That implies the velocity contribution is nothing but d by dt of x into theta. That is nothing but x into d theta by dt. That is nothing but x into theta dot. So we have velocity coming in because of the heaving motion and because of the pitching motion. And the total velocity, thus we can say total velocity is nothing but z dot plus x into theta dot. Okay, so that's our total velocity of the airfoil, or our total vertical velocity of the airfoil. So now let's start by calculating our kinetic energy. Kinetic energy, or T, we can write this as half m into v square, right? So now if we think about this, so let's say if we take any infinitesimal section of the airfoil dm, so we take a small section, so we can say minus b to plus b. If you remember, we have the semicolon from where we have defined x. So from minus b to plus b, if I take every single section of mass dm, I can integrate to get the total mass and into the velocity square. So x dot plus x into theta dot whole square. If I just expand and write this, so we'll just do some math here, mathematical algebraic manipulation, and write z dot square plus x square theta dot square plus 2 into x theta dot z dot, right? Or otherwise, if I just expand and write this, I can write it into 3 terms so that we can easily handle each of them at a time. And it half minus b to plus b of dm into z dot square plus half minus b to plus b of dm into 2x dot z dot theta dot. Sorry, no, not x dot, but just x here. 2x z dot theta dot plus minus b to plus b of dm of x square theta dot square. Just to make our life simple, let's try to look at each of these separately. So I'll call this as term 1, T1. I'll call this as term 2, T2. I'll call this as term T, T3. Okay. And then we'll try to simplify each of these terms and see how they would translate into giving us the total kinetic energy. Okay. So let's say, so our term T1 we said is nothing but minus b to plus b half dm into z dot square. Or z dot, I can say, is independent because it's a heaving motion, it is moving up and down, the entire airfoil is moving up and down. Z dot is independent of the x coordinate. So I can write, or the mass, independent of the mass, sorry, not the x coordinate, right, independent of the x coordinate. So I can write this as half z dot square minus b to plus b of dm. And this is nothing but the total mass of the airfoil. That means I can write T1 is half m into z dot square. So I'm initially first calculating, let's say, the term 1, and we easily know that if we take every infinitesimal section throughout the airfoil, then that would give us the mass of the airfoil, right? So a very simple term to calculate. So let's go ahead and try to calculate our term 2. So T2. So T2 is, we wrote this as half minus b to plus b dm into 2x z dot theta dot. I can remove z dot and theta dot are again independent of the x direction. So they are the same, doesn't matter where we are. So I can rewrite this as half into 2 into z dot into theta dot minus b to plus b of x into dm. Or other words, this can be written as z dot theta dot minus b to plus b of x into dm. Now we know that x into dm, this is nothing but the first moment of mass, right? So it's nothing but the first moment of mass. So let me call this as S into theta. Okay, so once I can write this, so that means that my term T1 essentially reduces to, sorry, T2 is theta z dot theta dot. So, okay, so now going ahead, let's try to look at the term T3 is half minus b to plus b of dm into x square theta dot square, or this is nothing but half. Again, I can remove the theta dot outside the integral of minus b to plus b of x square dm. And if you remember back from your earlier classes, this is nothing but the moment of inertia, right? The moment of inertia. I will call this as I theta, or in other words, I can write my T3 as half I theta into theta dot square. What I have done here is just some simple manipulation, mathematical manipulation, to kind of group our terms in such a way that I can conveniently write our kinetic energy. So once we are able to do that, so now if we try to go back and put all the three terms together, our total kinetic energy T is nothing but half, right? So into m into z dot square. So this is coming from our term 1 plus s theta into z dot into theta dot coming from our term 2, and half I theta into theta dot square from our term 3. So now we have found one term that we can use into our Lagrange equation. So we have the term that we need dt by dz dot, dt by dz, dt by d theta dot, and dt by d theta. We need to find these four terms for our Lagrange equation. So as we can see already, two of these terms go to 0. So we only have two other terms, and we will, as we go ahead, we will try to calculate these terms as well, so that we can get our equation of motion. So the next thing that we want to calculate is our spring energy. And the second part that we have is now the spring energy. If you remember our previous picture, as we have here, we have these springs that are giving the heaving, representing the heaving motion up and down, and this torsional spring that's representing the pitching motion, right? So we can write our total spring energy as two contributions. One is our let's say contribution from our heaving motion. So we are looking at our spring energy. We can write this to be equal to half. Let me represent this as uz, half into kz into z square. Similarly, we have our pitching motion, and this is represented by our torsional spring. Let's call this the energy stored in the spring as u theta is half k theta is into theta square, and our total spring energy u total is equal to uz plus u theta, or u is nothing but half kz into z square plus half k theta into theta square. Okay, so now we have already written our kinetic energy, we have written our spring energy, and one thing that we are still left out is to look at our generalized forces, right? So we will, in the next section, we will try to determine what is the lift, the pitching moment, and we will also try to determine what is the virtual work done and the generalized forces. So let's start by assuming that we already know that the lift and the pitching moment acting at the aerodynamic center. So our lift is L and our pitching moment is, there's a moment acting at our aerodynamic center. Let me just call it the moment at aerodynamic center. Let's say call it MAC. Okay, so without loss of generalization, for now I'll just assume this to be 0. We'll only focus on the lift part of it. So now if there's a very small rotation, delta theta, or then we can say that the net change in the height, right, but out of the flexural axis, okay, so for a small rotation delta theta, for a small rotation theta, net change in the height okay of flexural axis is z minus e into theta. If you remember from our picture, the flexural axis is behind. So for example, if there's a small change in theta, then the net change in the height is nothing but E is the distance between the flexural axis and the aerodynamic center. And there's a small change in theta, so the net change in the height is nothing but E into theta, right? Or in other words, we are approximating as tan, let's say the change in height because of rotation, let's say, from pitching is nothing but tan theta equal to, let's say, some h bar divided by E, which implies h bar is nothing but E tan theta, right? And since we are assuming very small rotations, that's approximately equal to E theta. And z is the downward direction. We are assuming theta is in the counterclockwise direction, so that's in E theta is upward direction, so the net change is z minus E theta. So if we had a infinitesimal rotation, for an infinitesimal rotation, change in height, right, we can say that is equal to d of z minus E into theta, that is nothing but dz minus E delta theta. Okay, so this is the net virtual displacement of the flexural axis. So let's call it as zz of flexural axis. Similarly, there can also be a virtual rotation, which we can say this is nothing but our virtual rotation. So this is our virtual displacement. And similarly, we can say delta theta as our virtual rotation. Okay, so let's use this idea that we have a very small displacement and rotation in order to calculate what would be the virtual work done from this. Okay, so the first step is we have a lift force. We have a lift force of L. So this lift force would be doing some virtual work. So we have some virtual work from the lift force. So let's say we call this as delta W lift. Okay, so let's say if we know this is nothing but the force into displacement. So that's nothing but lift times. So one thing we want to remember is our Z is defined in the downward direction, but our lift is defined in the upward direction. Okay, so then we can say add a minus sign here, delta of Z minus E into theta. Okay, so let's call this as WL. Second thing is we had this MAC moment that we had defined, and without loss of generalization, we said that MAC is 0. Moment about our aerodynamic axis we had defined as MAC. We defined this to be 0. So any work because of MAC is nothing but 0. Right? So now the last thing that we want to do is get our generalized forces. So generalized forces. So our net virtual work is work done because of lift plus work done because of the moment. And we said this is nothing but L into minus delta of Z minus E theta. Right? So now our generalized force QZ is nothing but dC, and Q theta is del W by del theta. So if we substitute, we get L minus L and L into E. Okay. So at this juncture, we have calculated all the quantities that we need to write our overall final equation of motion. We have the kinetic energy, we have the spring energy, and we have the generalized forces. We assume that there's no dissipation drag, that D coming into the equation itself. Let's in the next step try to write our equation of motion and try to derive all the quantities that we need. For example, we have not yet done for the kinetic and derivatives of the kinetic energy and the potential energy. Let us do these derivatives and get our equation of motion from them.